The today's tutorial topic is SHARP. The SHARP stands for a Scalable Hierarchical Aggregated Reduction Protocol. It's an in-network technology from Mellanox to offload computation from host to the network. So this technology is basically to improve the performance of HPC as well as artificial intelligent AI workloads. So how can we optimize the HPC applications? So the key is one of the major time spent in the HPC applications is the MPI collectives. And so by offloading the collectives from CPU to some CPU, we can make CPU available for the compute, so we can at the same time overlap the communication and the computation. So this essentially will improve the application performance. At the same time, if you take today's distributed deep learning frameworks, the key is to how fast we can synchronize the gradients and each step to make it our training faster. So still, again, it's a common primitive, so all reduce. So it's how fast we can do that to decrease the time of each step and increase the total training time. So the SHARP is a common technology for both HPC and AI to improve the performance. So SHARP allows to offload the operations from CPU to the network. Some of the common aggregation operations are all reduce. It's a vector operation. You spread the results from the group within the group, and reduce, it is same like all reduce, but the result is distributed to a single entity. Like gather and all gather is a vector concatenation operations. So these are some key aggregation operations used in most of the HPC applications as well as AI. So what algorithms we have today for the host-based? So it's generally we use the tree-based algorithms for the collectives. So it's many to one and one to many traffic patterns. So, but this is not a good for in the scale-out clusters, in a big clusters, because when the tree nodes might, the communication might be, it might go through the different levels of the tree, and it can cause a congestion, as well as scale increases, the tree radixes, the fabric tree, it requires a higher level of the tree in the fabric, and the results distribution is again either you have to use the tree-based algorithms or multicast-based solutions to distribute distribution. So this is the common tree-based algorithms existed today. So for example, if you take the all reduce, let's take the recursive doubling here. Here data is recursively divided and processed on the CPU, and after that it distributed again to everybody. So it's here when the data is exchanged between the ranks, the CPU has to perform the reduction operations. So your CPU is consumed there, as well as, so you have to send the data at least 2x times, because it consumes twice the amount of bandwidth. For example, here the 4 nodes, it's a log n steps, so it's 2 steps for reduction and then 2 steps for all gather your results to everybody. So in each step, for example, in the step 1, rank 1 is sent its data to rank 2 is sent its data to rank 1. Now CPU has involved there, so to perform the reduction, then to go to the next step. So for example, if your application is is involved computation at the same time if you not give enough resources, enough CPU resource for the computation, this reduction. So your whole step is blocked there, and you won't progress to the next step. So it will cause a overall increase in the latency of all reduce, and it will essentially affects your application performance. So how can we solve this problem? So the solution the Mellanox have is a offload technology. So here we aggregate the data while we move the data into the while the data is moving in the fabric. So essentially we are making a network as a coprocessor, or it's a coprocessor. So it also reduces the amount of data running through the network. For example, if earlier recursive doubling, it is taking 2x bandwidth, but here while data is moving up in your fabric, you do the computation on the data, and the end rank process just has to wait for the final result. It doesn't have to do any kind of reduction, or it doesn't involve any log n steps, or it just pushes the data to the network and waits for the results. So it will reduce the latency because the data is going through shorter path. There is no involvement of the CPU, and the operation is fully offloaded to the fabric. So for example, here if I compare sharp versus non-sharp, sharp versus no sharp. For example, recursive doubling in the reduction phase. So in the first step, here the blue end nodes are shared memory ranks, and the only one rank from each node is participating in the network. So you kind of do first in-node reduction, then a node leader from each node is participating in the all reduce. Once the final data is there, you distribute the data within the node. So while it's doing the node leaders are doing the all reduce. So in the first step, so the neighbors are exchanged. The next step 2, the next log n distance ranks are exchanged. So here you kind of 2 steps. Each rank is involved in the 2 steps, and the computation is performed on the CPU. Whereas in the sharp case, each node, it puts the data to the network. So the common ancestor for the switch here in the fabric, it performs the final computation, and it sends it back the results down the tree. So this way, the computation is fully offloaded to the network. So what kind of benefits you can see? For example, here the 128 nodes, if you see the 8 bytes, the left side is 8 bytes and 128 byte all reduce. So you kind of see a flat latency with the sharp, because you push the data to the network in the same. I mean, for 8 bytes, 128 bytes, it's a single message, so it takes the almost same amount of latency. Whereas if you take the host-based solution, it is increasing as it is scaling, because it is logarithmic number of steps, and the host process is involved. It's a simple benchmark. It doesn't have any computation, but in the real application, there might be the application computation might be interfering with the communication progress. So with the sharp, you basically offload and have a kind of linear performance as it scale out. So the right side have a bigger payloads. It's 1 kilobytes and 2 kilobytes. This, if you see, so this is at a larger scale on Toronto, University of Toronto cluster. We have a 1,500 nodes, and it's running 60K MPI ranks in Dragonfly topology. So you can see that the sharp, it's kind of, it maintained its advantage, low latency, because the latency will change only when the in the switch, in the fabric, if the number of levels of the fabric levels is increases, then it increases the, it adds up the switch to switch latency. But otherwise, it maintains a constant linear latency here. You can see the same right side with full PPN also, because when you're running the more number of ranks per node, here it's the 40 ranks per node. So within the node, it has this constant reduction cost across all the nodes. Then the only variation factor is the node leaders participating in the all reduce. So that is essentially will turn into a PPN1 problem. So that's how the sharp will help even when running the more number of ranks per node. So how does this work? So the sharp is it's a general purpose primitive. We designed by keeping in mind of HPC and AI. It's applicable to multiple use cases. So it is a in-network tree-based aggregation, and it supports a large number of groups, and it also supports simultaneously multiple outstanding operations. It's not like only one operation at a time or one group at a time. So we have a highly parallelized aggregation. It supports large number of groups and a large number of outstanding operations. So, and if you take the HPC applications, what kind of operations we can offload? We can offload barrier, reduce, all reduce, and bcast, broadcast. And when it comes to aggregation, we can do the sum, min, max, min location, max location, or XOR, and all the MPI supported operations are supported in sharp as well. So it also supports multiple data types, floating point 16, floating point 32, 64, as well as integer 16, 32, and 64 bit. So for the small messages, it supports up to 1 kilobyte payloads per message per operation. We also have a latest feature in the HDR generation switches, that is quantum, that's streaming aggregation. So we can perform the aggregation, and the very high bandwidth mode is equal to the line rate. So you can push very large messages, and we can expect the full bandwidth of the network. And also we support machine learning use cases. The sharp supports CUDA and GPU Direct RDMA. I will explain that in next couple of slides, but it's built by keeping in mind both application, HPC as well as machine learning applications. So the sharp tree is a logical construct on the physical topology. So it constructs a tree logically by considering the what nodes involved in the MPI job or in your AI job. So it takes the physical topology. On top of that, it constructs a logical tree, and it can support many trees simultaneously. And here the tree links are implemented on top of hybrid transport, reliable RC connections, and within the tree, the network is identify the operation based on the group ID and the sequence number within the operations. So if you construct a group, it's like an MPI concept. So you can have many communicators, and within the communicators, the data is ordered by sequence number, and it supports multiple communicators and multiple jobs. So the principles of operations is, for example, here So the end nodes are, while end nodes are pushing the data to the network through the aggregation request, the data is stored in the first level of the, if multiple ranks, multiple nodes under the switch is participating in that group, then the data is it's aggregated in the switch when the data is arrived from all the ranks, all the processes requesting under that switch. So here data is aggregated, then that is pushed up to the fabric. So similarly, the data is aggregated and at this level of the switch because this is the common ancestor for all the ranks participating in that group. Once this switch is done, it moved up to the next level of the switch. So here final data is aggregated, and then similarly the data will be pushed down to the end nodes. So the end processes just has to push the data and wait for the results. So they don't need to do any computation. So another key technology is the GPU Direct RDMA to accelerate the HPC as well as deep learning frameworks. So with this GPU Direct RDMA technology, the Mellanox network adapter can directly read data from the GPU memory. So earlier, when the GPU Direct RDMA was not there, so the data has to stage to the host memory, then host memory to the adapter, then adapter to the remote adapter, but then remote side again to the CPU memory, then from CPU memory to the GPU memory. So there was a lot of levels, and its latency is very high in that case. So with GPU Direct RDMA, the PCI device, the adapter, can directly read the data from the GPU memory. So it avoids the copies through the host, and it eliminates the CPU bandwidth and latency bottlenecks, and uses the RDMA transfers between the GPUs. It's significantly reduced the MPI message latencies from local GPU to the remote GPU. It's one point. With the InfiniBand and NVIDIA GPU, it's around 2 microseconds. Compared to with CPU staging, it is 20 microseconds. So the huge advantage is the latency is reduced significantly. And it also allows the asynchronous communication, and as well as it frees the CPU from copying data from GPU, as well as push and move the data to the network. So here the advantage. So we can use the GPU Direct RDMA technology with the SHARP as well. We can directly read the data from GPU and push the data to the network, and the network does the compute part, and it directly puts the data to the GPU. So for example, here here TensorFlow and of<silence>oad run. ofǀoad is a distributed TensorFlow framework. It's running a ResNet 50 benchmark on NVIDIA P100s, and so here you can see that on 8 nodes and 16 GPUs. So we compared Nickel with the SHARP. So here Nickel is a collective library, GPU collective library from NVIDIA, highly optimized one. We compared Nickel versus SHARP here. So we can see that the scale of 16 GPUs, we already see a 12% increase in the performance. So at the 22 GPUs, we got 16%. So the reason is, the 16 GPUs, when you are exchanging, if you want to compute, so when you move the data to the GPU, you have to launch the kernel to do the compute part. So whereas with the SHARP, you don't have any computation in the GPU for the reductions. You just push the data from the GPU to the network will take care of the compute, and you directly placing the data to the GPU. So with the GPU Direct RDMA. So the next, I will give you a little brief overview on the Sharp software. So Mellanox has a HPC X scalable HPC software toolkit. So it is a complete MPI and PGAS and UPC packages. So it has a pre-built binaries of MPI and other middlewares, which includes the Sharp, and which gives the best out-of-box experience. It is both for commercial as well as open source applications. So it includes OpenMPI and the UCX. It's a highly optimized InfiniBand communication library, and FCA. It's a and it's FCA. The other name is HCOLL. It's a highly optimized collective library from Mellanox. Sharp. So it's a general purpose aggregation software, and we have some profiling tools and benchmarks in HPCX. So where does Sharp sits in the MPI stack? So you have it on top, you have a MPI. For example, if you take the OpenMPI, it has a collective frameworks. You can plug in any collective frameworks into it. So HCOLL. And we integrated Sharp into the HCOLL. So if anybody would wants to use Sharp, they can integrate HCOLL directly. So users will get Sharp features along with the other optimized collective performance. And so HCOLL, for example, it's already integrated into multiple MPI libraries like OpenMPI and MPitch and MWAPitch. And Sharp also, if users would like to have their own integration, the Sharp provides a high-level API, which is easy to integrate. It just have I think you just need to sharpen it, and Sharp communicator create and Sharp communicator destroy and Sharp finalize. It's just, you have a bunch of just 4 to 5 API calls. All you need to do integrate Sharp into any communication framework. So in the fabric, so what are the software components we have for Sharp? So there are a couple of daemons needed for Sharp support. So on the subnet manager, so you need to run aggregation manager daemon, which is a central entity which which controls the Sharp resources in the fabric. So allocation of the groups and allocation of the buffers and so on. And each compute node has a Sharp D daemon, which is which is mostly in sleeping mode, which don't consume any resources. When MPI job is running, the one rank will contact with the Sharp daemon. The Sharp daemon will ask the resources from aggregation manager, and once the resources are there, then MPI job will directly talk to the aggregation nodes. Aggregation nodes here is a switch in the fabric. So the process directly sends the message and receives the message from the switch. So it's a very simple way to enable the Sharp in the fabric. In the OpenSM, there is a flag called Sharp enable. So just set that flag and run it. So you will see a virtual port in the IBNet discover saying that Mellanox aggregation node. It tells that Mellanox Technologies aggregation node. So that means switch is enabled with the Sharp support. And if you are using the MPI, OpenMPI and HCOLL, so there are a couple of flags to enable the Sharp, and there are some thresholds to at what scale you want to enable the Sharp. For example, if your communicator size is only 2 ranks, probably you don't want to waste the resources. So you can set the thresholds at what communicator size you want to use the sharp support. And also, so in the quantum, the latest quantum hardware, so we have a streaming aggregation, which is highly optimal for the bandwidth large messages. And so a application can also ask for a specific amount of resources in the, so I mean, as I said, there are groups and operations. So sharp supports multiple groups. So if your application is have a lot of communicators, you can ask for more groups than the default quota assigned for that job, because in advance we don't know, I mean, the sharp aggregation manager don't know how many communicators the application is going to create. So it gives the default quota, but users can change the resources they needed from the fabric. So number of groups they want, number of operations they want to execute. So I have a small demo. Yeah. Okay. How can this go? One second. So I have a small setup with our latest HDR hardware. So so I have 4 nodes here. Each one is it's a DGX one kind of box. It has 8 GPUs and 4 NICs. It's a 2 HDR dual port cards is running. It's running in EDR speed. And so the here this is my subnet manager node. Here I have a OpenSM running with the sharp enabled. So you can check. So I've been at Discover. You can see that you will see one virtual port saying that aggregation. It's an aggregation node. So that means the switch has a sharp capabilities. So I'm using node 61, 62, 63, and 64. So each one has a 4 HCAs. So each one is running at the EDR speed. And the compute nodes, each compute node is running a sharp daemon. And here I would like to show you OSU micro benchmark, OSU already used performance, as well as a Horovod TensorFlow with resonate benchmark, nickel versus sharp. So I prepared scripts basically. So it's a MPI run, the number of ranks. I'm running a PPN1 mode here. And I'm running up to 512 megabytes to show the benefit of streaming aggregation. Okay, let's have a bunch of flags to enable the sharps. Some of them are default, but I explicitly enabled here to have a idea of what else we need to change if we want to a custom amount of resources. So the first case I'm running without sharp. So this uses still optimized HCOLL all reduce, but it's a host based. It's a four ranks. Yeah, by default, OSU runs up to 4 megabytes, but benchmark runs. But I changed it to 512 to see the advantage of streaming aggregation. So we nearly got 190 milliseconds for 512 megabytes. So now running with the Sharp, so HCOLL enable Sharp. So have some debug info here. So when I'm creating the job, I requested, OST means outstanding transactions, mean how many operations it can parallelly run, and how many max groups 0 means give me the default number of groups, and number of trees it's 1. Then the job is so I got the tree from the with the resources of 128 OSTs, as well as maximum payload it can run is for small messages 1 kilobyte. Maximum number of groups it can create is 128 groups. So as well as along with the low latency tree, we have two type of trees here: low latency tree and streaming aggregation tree. It also created a streaming aggregation because I enabled it, and I want to see the benefit of it in the large message. So for 512, it ran in 65 milliseconds. So it's almost 3x performance difference compared to the host-based. The mainly due to the only at the 4 ranks. So as it scales out, so you would see this. This should be the constant because it's a matter of the network topology. As long as it maintains the linear latency. But whereas if you go to the host based, as you scale out, your log and steps will increase, and it depends upon if your CPU is free for do the computation part. So you might get a different results. So this is one, and also I have a same OSU benchmark running in CUDA mode. So I compiled OSU micro benchmarks with CUDA, and I enabled. I'm running. Okay, so I'm running OS all reduce with CUDA flag. So I'm running up to 512 megabytes. So in this case, it's using both technologies, Sharp as well as GPU Direct RDMA. So when you're streaming, the data is directly got it from GPU buffer. So the first case is the nickel. This I'm running with the nickel. So which is highly optimized for GPU case, and now it's running with Sharp now. So you can see that a small message, the latency is 4 microseconds, whereas the nickel case it was 30 microseconds, because most of the cost is coming from launching the kernel to reduce the data. So even though you have a 4 bytes, when you get that 4 bytes when you get that 4 bytes from other ranks to your place, you need to launch the kernel to compute that. So whereas in the Sharp case, so the host is not doing the GPU is not doing any kind of computation. So you don't have any kernels at all. So the HCA directly read the data from the GPU, and it's pushed to the network, and network is computed, and you directly got the results. So even at the larger scale, so it's still it's a 50% better than the nickel. So any questions? So I have a So here I compiled ofɁoad with ofݴoad. It's running TensorFlow on TensorFlow 1.12. So, and here the scenario is I'm running 16 number of processes, 16 GPUs. Each node have using 4 GPUs and 4 NICs. And yeah, that's it. So I'm running the synthetic benchmark of ResNet 50, and the batch size is 50, and it's using the GPUs. So I have two cases to run here. One is the nickel, so it's using the almost default settings, and I have a sharp. Yeah, it would take, I think, 1 minute. So first, it's running with the nickel library. A bunch of warnings from TensorFlow. So this is Volta GPUs, and and they have the NVLink in between them. So nickel uses the NVLink features, and it is highly optimized for that. So on my 16 GPUs, I got the results is it trained 4,315 images per second. The same test case I'm running with sharp streaming aggregation. We it is 4,674 images per second at this scale. So it's roughly, I think, 10 to 12% types. So yeah, so we ran OSU micro benchmarks as well as here the ofɁoad. So the primitive we have a common offload primitive, that is the sharp. And it optimizes both HPC as well as AI workloads. So it's a general purpose aggregation protocol. It multiple frameworks as well as HPC applications can use to accelerate their performance. So, yeah, this is the demo I used just now. It's 4 nodes and 16 GPUs. And I used nickel as well as it has a 16 Volta NVIDIA GPUs and running on Ubuntu Mellanox ofɁoad. And we saw these performances for already used for CPU case with the low latency with 4 versus 2 microseconds. And at the large message side, we almost saw the 3x performance difference with the streaming aggregation. And also, Sharp can use the GPU Direct RDMA. So we compared nickel versus Sharp. The small message we had seen the 10x performance results here. And ofݴoad ResNet 50. The ideal was 4,700 images per second. So we nearly got 95% of efficiency with the Sharp. So compared to the nickel's 88%. So yeah. So the main advantage is offloading compute from CPU as well as GPU and push that to the network, and the fabric will take care of the computation while data is moving into the network and the end process has to see just the results. They don't have to worry about scheduling issues as well as costly kernel launchings in the GPU case. So, any questions?
Have you done anything with the RDMA of Ohio University that you actually have run Spark or these things? What would be the benefits that you bring to the presentation we got yesterday from you?
Unfortunately, yesterday I was not there, so I will check it and get back to you.
Yeah. Because DK has a way of in Hadoop.
Okay. So
to replace IP with RDMA.
Mm-hmm.
And he reduces latency.
Yes.
Therefore, he increases
okay.
performance.
Mm-hmm. Mm-hmm.
It would be fantastic for you to share those kind of results.
Sure.
In collaboration with the client.
Mm-hmm.
Thank you.
Does your in-network aggregation work with both types of 16-bit floating point, the float 16 and the FP16?
It complies to the IEEE standard. I mean,
float 16 is one style, and FP16 is a different, and they differ by the bit in the hex code.
Okay, I have to check that, but as far as I know, it's a IEEE compliant floating point representation for 16. So yeah, it is in line with the NVIDIA's GPU FP16 support. Yeah.
I may have missed something, I'm not sure. Is this strictly a software solution, or is there some, is there a specialized hardware involved?
It's a hardware, so because it's offloaded to the hardware, right? So your computation is actually happening in the switch IC. Yeah. Flattery, Dragonfly, those two are the ones as far as I know. Gillard might have. You can check it. So that is inside the box. So that is fine as long as. So if you take the nickel, right, today it does the ring inside the, it does the ring. Okay, so it does the file, it takes the data from one HCA and it pushes other same HCA or different HCA. So within the DGX, you have while moving in the ring, it computes, and for only when it goes out of the node, the IB, the communication part is involved. Okay, if you have any tree-based algorithms, you can do a reduction within the box, within the DGX. Now you have aggregated result at one place, and you can push that to the network. No. It's just a control path. When you create the job, right, you need some resources from the, hardware. So the MPI process talks to the daemon or Unix sockets, and that talks to the aggregation manager. It allocates the resources, that's it. When you create the job and create the communicate. When actual collective is happening, so the MPI rank opens a QP to the switch, and it directly talks with that. It puts the packets directly to the network.